It's my great honor to present my work, Bootstrap the Lattice Yang-Mills theory, collaborated with my PhD supervisor, Vladimir Kazakov, who is the real expert in matrix model and integrability and who teach me a lot during this project. This work is a direct follow-up of Anderson and Kruczynski they did in 2017. Martin also gave several lectures on this topic last week. So although I will be as self-contained as much as possible, when it comes to the topic that's already covered by Martin last week, I will be brief. And feel free to stop me at any moment if you have any questions about it. Okay, let's begin. So the bootstrap method, it is basically solving the problems in theoretical physics by the optimization theory. A simple example of optimization theory is the semi-definite programming, which we will use a lot of times during this project. That is, we minimize linear combination of variables subject to some linear semi-definiteness of a linear matrix. And this kind of semi-definite programming, or SDP, it falls into the class of convex optimization. Generally, we cannot solve a large-scale non-convex optimization problem. It's like solving a linear system of equation or nonlinear system of equations. They are on different level of complexity. Solving convex optimization or non-convex optimization, they are on different level of complexity. So we should keep it in mind because we will see some non-convex things later. Okay, let's start with some a simplest bootstrap model or a toy model or a prototype of all our method in this project. That is, if you like to call it, it is a zero-dimensional phi-4 theory. It is nothing but a quartic integral, an exponential integration over quartic potential. Everyone knows how to solve it both analytically and numerically. But here we are going to use bootstrap method to solve it. Here, our goal is, or our observable is case moment under this partition function, equation 4. That is x to the k integrated over this quartic integral. For the bootstrap method, first we notice that there are Schwinger-Dyson equations, which we will get from do an infinitesimal variation by changing x to the x plus epsilon. Or we can get such equation by integration by part. Anyway, it is equation 6, which is a linear recursion relation relates with different moments of the partition function. And we also have the global symmetry, which means that all the old moments, they are 0. This is just because the symmetry of the original partition function. Although this seems naive, you cannot derive the global symmetry just by the recursion relations. They are totally different. So by these two equations, we can actually solve all the higher moments. Of course, the higher even moments, all the moments they vanish. We can solve all the higher even moments as a linear function of W2. Okay. So what else? To solve the W2, we don't have any information from the Schwinger-Dyson equation or the global symmetry. Here we propose to consider the following inequality, that we integrating the measure against the square of any polynomial of x. Then this must be positive. Why? Because you are integrating a positive function against a positive measure. This is definitely positive. But we notice that this must be true for any polynomial. And this polynomial, we can formulate this condition, equation 8, in terms of a quadratic form in terms of vector alpha. So for any alpha, this is true, which means that this is a positive positive semi-definite quadratic form. And the matrix in the middle of the quadratic form, it must be positive semi-definite. So this is equation 9. This is the matrix in terms of all the moments of the partition function. And we notice that the old moments, it vanished. So there is actually a lot of zeros inside. And we notice that the higher moments, they are linear functions of W2. So this infinite dimensional positive semi-definite matrix, it is actually a linear inequality on W2. This condition will be referred to as positivity of the correlation matrix because it is a matrix of correlators. Okay, so how to do the bootstrap? Here, we can make a truncation of that correlation matrix, infinite dimensional, to truncate it to the top lambda plus 1 times lambda plus 1 some matrix of W. And we can minimize or maximize W2. This is a semi-definite programming already. So how it will work? For this simplest model, we have the analytical result for reference here. Everyone can get it by just typing the integration into Mathematica. And if you put G equals 1 and lambda equals 10, we can also get the bootstrap result. So the number on the left-hand side is when we minimize W2 under the inequality. And on the right-hand side, it is maximize W2 on the inequality. So we see that in the middle, this is the exact value. So we get that our bootstrap result, it is actually highly non-trivial. We get already for lambda equals 10, we get 6 digits already. So this the result is highly non-trivial. And for different G, you can see that in the middle, the dashed line is the analytical result. And when you are increasing the lambda, the allowed region for W2, it is shrinking very, very fast. Actually, for lambda equals 5, which I didn't plot here, it is already indistinguishable from the plot. Okay, for this toy model, I have a final remark. As you have noticed, there is a lot of zeros in the correlation matrix. Actually, we can rearrange the indexes of the matrix and put it into a block diagonal form. The first block corresponds to the square of the even moment, and the second block corresponds to the square of the odd moment. Although they look similar, actually they are independent from each other. Why this happened, I can tell you at the moment that this is because even powers of x and odd powers of x differs into different representations of Z2 symmetry. You remember that Z2 symmetry is a symmetry of this model. And what I want to indicate here is that if we have more non-trivial global symmetries, then we will have for each irreducible representation of the global symmetry, we will have a independent block for that symmetry. This is what we will discuss for Yang-Mills. Later, I want to show you that this method, this bootstrap method, it is actually a serious numerical method. Look at this model. This is a 2-matrix model in the large N limit. So this is already an integration with infinite number of degree of freedom. And to the best of our knowledge, this 2-matrix model is not solvable. And if we use above method for this model, at lambda equals 11, which means that we are doing the bootstrapping over all the moments in terms of A and B with length less than 22, and with G equals H equals 1, then we have a 6-digit result. Here, the plot is a shrinking of the island of the trace A to the 2 and the trace A to the 4th. Okay, so from some studies, we already get that this precision we got is actually better than the Monte Carlo, actually much better than the Monte Carlo precision we could get for the large N matrix model. Okay, let's go to the main topics of this project. That is large N Yang-Mills model, large N Yang-Mills model on the lattice. Here, this is the traditional Wilson action, and we are doing the integration over a 2-dimensional, 3-dimensional, or 4-dimensional space-time lattice. And our goal here is to bootstrap the 1 plaquette average here. I can show you the result first. here the result is 3D and 4D result. And the yellow region, the orange line and the blue line, they are the rigorous upper bound and the lower bound of the one plaquette average. The dashed line is the perturbation result, both in the weak coupling limit and the strong coupling limit. And the red dot, they are the Monte Carlo result, and also the purple dot. So you see that especially in 4D, which is most interesting, we are, especially in the weak coupling limit, we already get a very, very precise result. So later I will describe how to get such a result. Actually, all the method goes very parallel to the toy model. Let's look at it. For the observable, for the toy model, we are bootstrapping the case moment. And for the lattice Yang-Mills, we are doing the same things for Wilson loops. Actually, expectation of Wilson loops. And for the action, for the toy model, we have quartic action, but for Yang-Mills, we have the Wilson action. The equation of motion, they are both just Schwinger-Dyson equations. For toy model, there are some linear recursion relations. But for the lattice Yang-Mills, it is the so-called MAKEENKO-MIGDAL loop equations. There are some equations relating different Wilson loops. For the symmetry, the toy model symmetry is Z2, we already described. But for the lattice Yang-Mills, we have the lattice symmetry, plus the C here denotes the charge conjugation symmetry. Actually, it is reversing the Wilson loop. That means Wilson loop, whether it goes one way around or the other way around, they have the same expectation value. For the positivity, for the toy model, it is a Hankel shape matrix. But for the lattice Yang-Mills, actually we have more positivity conditions. One of the positivity conditions is just like the old one, that is by Hermitian conjugation, we get the product. Actually, we have more positivity conditions I will describe. And for the convexity, for toy model, it is a perfect convex optimization problem. But we will see that due to the large n factorization, the loop equations, they are not linear. So this is actually not a convex problem. We need to do some convex relaxation to make it perfect SDP. Okay, let's begin. First, we begin with the MAKEENKO-MIGDAL loop equation. Martin has already described this subject last week, so I will be very brief here. Here is a loop variation corresponding to the link we are doing the variation. Here I just give you several simplest examples in two-dimensional lattice, how the loop equation will look like. This is when we are doing the variation on a link of the single plaquette, we will get such a loop equation. And we also have the backtrack loop equation. We see that if we put a backtrack on the margin of the one plaquette and doing the variation on this link, although without variation, this new Wilson loop, it is exactly identical to the one plaquette due to the unitarity. But when doing the variation, they are different. It gives non-trivial loop equations. The backtrack can be infinitely long, actually. So you can imagine there is very long backtracks starting from a non-trivial Wilson loop. Okay, this Wilson loop, the figure 8, it looks like number 8. This is the one of the lowest order nonlinear loop equations. So the nonlinear terms, it only appear when we have overlapping links. Okay, this finished our very brief introduction to the loop equations. For the positivity conditions, suppose we must take some, let's say, several Wilson paths starting from the same point and end at the same point. Here, for the simplest example, we get the it starts from 0, 0 point and end at 1, 1 point. And we use a very similar method to the toy model, and we can get such a positivity matrix. This positivity matrix is quite trivial. If you try to solve it, it just means that the absolute value of UP, it is less than 1. Of course, this is trivial. But let's say a non-trivial case that in the two-dimensional, case, we consider all the Wilson paths coming from 0 and end at 0, but with a length cut of 4. So this is a Wilson, this is the positivity matrix correspond to it. The one here, it corresponds to the length 0 Wilson path starting from 0 and end at 0. And for the other indexes, there are different paths coming from 0 and end at 0 with length 4. So this is a 9 times 9 positivity matrix. And actually, it gives us non-trivial bound. We will see. For this matrix, there are all in 6 Wilson loops inside the matrix. And these 6 variables, they are related by 2 loop equations, which we already wrote down. This is a 2 loop equations. And then this is a well-defined SDP. We can do the optimization. And we can, after putting lambda equals 1, for example, you can put lambda any other value, that doesn't matter. If we put lambda equals 1 at this lowest order bootstrap, we will get the 1 placket average larger than 0 and smaller than 0.693. Okay, but if we aim for higher order bootstrap problem, the complexity goes up exponentially. So we must come up with some ideas how to simplify this scheme. One of the complications is that for higher order loop equations, they are nonlinear. And also the matrix, it grows exponentially. And we may have more positivity conditions due to our problem is already much more involved. It's not surprising we have more positivity conditions. Here is a new positivity conditions. It is the reflection positivity actually. We can not only get a guaranteed positive quantity by taking the Hermitian conjugation, but we can also get the positivity, guaranteed positive Wilson loop by the space-time reflection showed by these 3 figures. So there are actually 3 times of such reflection positivity: reflection by link, reflection by the side, and reflection by the diagonal. So if you take linear combinations, you can imagine that there are 3 more positivity matrices here. And this kind of new positivity conditions, they are actually independent from the old one. Look at the gray curve and the orange curve here. The gray curve is the bootstrap without reflection positivity. And the orange curve, they are the bootstrap with the reflection positivity. Apparently, they are at the same order. They are L max equals 12, which means that we are doing the bootstrap with all the Wilson loops with length less than 12. So it is obviously that they are independent. Okay, let's look at the lattice symmetry reduction. Already from the very similar topic, conformal bootstrap and S-matrix bootstrap, we know that the positivity condition, they are arranged to different spin channels. So it is not really surprising that on the lattice, our positivity conditions, they are arranged in different irreducible representations of the global symmetry or the lattice symmetry. This is a lattice symmetry group for different kind of different dimensions. I must notice you that for the reflection positivity, we have less symmetry because the reflection plane, it damaged some part of the global symmetry. So we are, for the reflection matrix, we are doing the symmetry reduction with respect to the subgroup which stabilize the reflection plane. This is detail, just detail. Let's look at this matrix again and see how the symmetry reduction works here. So we can take linear combinations of different Wilson lines and to put them into different representations of two-dimensional point group of the lattice. And we take the inner product here to get the inequality condition. The linear combination fall into the different irreducible representations. They are, by the group theoretical construction, they are orthogonal to each other. So we get block for each irreducible representations here. So this series of very simple equality, this is actually exactly equivalent to the old 9 times 9 positivity condition. So this greatly simplifies the problem. And also the relaxation. I don't want to spend too much time because the time is, I'm already running out of time. Let's look at suppose we have a single quadratic term in the loop equation, and we introduce a new variable, let's call it T1 in the place of the quadratic term. So we note that x squared equals T1. This is a non-convex condition. Why? Because all the nonlinear inequality, they are generally non-convex. But we notice that x squared smaller than T1, smaller or equal than T1, this is convex. Why? Because we can rewrite them in terms of semi-definite matrix form. This is definitely convex. So by this, what we have done, we have forget T1 is a square of x, but this new variable T1 is subject to a positive semi-definite matrix. This could be generalized to a vector case. That means here the x is a column vector. Suppose the x is a column vector of the Wilson loop, and we introduce a new variable or new matrix in the place of the quadratic terms in the loop equations. And then we forget they are the quadratic terms of the Wilson loop, but they subject to the new relaxation matrix positivity condition, that is equation 34. So we introduce some new variable, and this subject to the new positivity conditions to make the whole system convex. This is how the relaxation works. For example, for our Yang-Mills bootstrap at Lmax equals 12, our correlation matrix, our relaxation matrix is this 2 times 2 matrix. Here the Q is a variable in the place of square of 1 plaquette average. Okay, then we finish. This is our final scheme. We minimize or maximize the 1 plaquette average to get the rigorous upper bound and lower bound. This is subject to the condition of MAKEENKO-MIGDAL loop equation, and also the correlation matrix factorized with irreducible representations of the global symmetry, and also 3 kinds of reflection positivity matrix also factorized with respect to the irreducible representation, and finally the relaxation matrix. This concludes our construction of the scheme. Okay, this is the result of our bootstrap. For 2D, I notice you that the large N Yang-Mills on 2D dimensional, this is exactly solvable. And the UP here, the equation 37 is the exact solution of UP. And here, this is in the plot, this is our bootstrap result. The yellow, orange, and the blue line, they are the shrinking allowed region when we are increasing the bootstrap cutoff. Actually, this is instant. This doesn't take any time to finish this plot. But for 3D and 4D, the complexity grows exponentially. So if this takes, let me say, for 4D, for each single point on the plot, it takes approximately 20 hours to finish it, 20 hours CPU time. Okay, so let's look at the final plot. For 4D, as I already said, in the weak coupling phase, our bootstrap upper bound is very close to the Monte Carlo result. Actually, in the weak coupling limit, it is already better than the Monte Carlo result. And it goes very close to the perturbation line. This is a third order perturbation line. Okay. Yeah, for the I also must notice you that for the weak coupling phase, this is a physically important phase. For the strong coupling phase, it doesn't flow to the continuous QCD when n equals 3. So this is less important here, actually. Okay, we are close to finish. This is some future directions which I want to mention. And this is actually the ongoing directions. The first 2 points, I think it will, we will get some results very soon. The first one is technically our algorithm, still it is much perfectible. For example, the positivity conditions, that means that the positivity matrix, it is unlikely that the whole positivity matrix, it contains all the part of it is equally important. This is very likely that a very small part of the positivity condition, it already contains 99% of the information. So we need to come up with a very clever way to select the positivity condition. When this is done, we can easily push the bootstrap cutoff to L max equals 24. At this cutoff, we expect that we will have precision very close to the Monte Carlo maybe. The second point is our scheme. This is not at all limited to large n, as you can see from the toy model. This is actually, as long as you have a positive measure, this will work. So we can expect that we can directly bootstrap matrix model like in n equals 2 and n equals 3, which means FU2 matrix model, FU3 matrix model, or FU2 and FU3 lattice Yang-Mills theory. And the third one, here, unlike Monte Carlo, it has some finite space or finite volume finite volume uncertainty or statistical uncertainty. All our bounds, they are rigorous. But if we don't insist on such rigorous margin, we expect that we should get more precise result. Actually, this demands us on a new effective action to minimize. We are not anymore minimizing the plaquette average, minimizing or maximizing the plaquette average, but we need to figure out some new effective action to minimize. If this is done, then we have more precision even at L max equals 16. Okay, I'm finished. Any question?
Okay. Thank you.
I have one question.
Yes.
So I'm wondering whether anybody has supersymmetrized the loop equations.
Yes. I think Martin tried it, but I didn't follow that part of his work. If you can ask Martin directly how this works, but it seems generalizing this story to the supersymmetric Yang-Mills theory, this is not trivial. It seems not.
It doesn't have to be supersymmetric Yang-Mills. It could be some simple supersymmetric model. For example, you showed these quartic models. One can supersymmetrize that.
Yes, then simple. Of course, I think it will work. There is actually someone tried to bootstrap the fermionic system already. You can follow such work. So fermionic there is no problem. So I don't think there will be any problem with supersymmetric things.
Okay, thanks.
Yes.
Masanori.
Yeah, is it possible to avoid sign problem in this approach?
Yeah, this is a very good question. This is an open question because till now we didn't seriously tried models with sign problem. The Hermitian conjugation for the models with sign problem, it may be problematic, but the reflection positivity, it seems it still holds even if there is a sign problem. So this is possible that this method, after some modification, it still work. Yeah, this is open till now.
Yeah, I asked in many supersymmetric theories, we do sign phase quench simulation, and somehow it's working, but if you can somehow justify it, it could be fine. So
yeah, this is a very interesting future direction. I agree.
I have a question. question
Yes.
about this going to the continuum limit. The single plaquette is, I think, I mean, it's at the cutoff, right?
Yes, it's a UV quantity actually.
So I would think to get the information you want that is universal rather than specific to the action, you would want to probe something at a correlation length which represents continuum physics. Is that what you were saying that you would try to do?
I mean, we are bootstrapping the single plaquette, which is the UV quantity. But
Right.
at the same time, you can bootstrap.
Right, but I can change the
higher
action. I can change the action almost arbitrarily at that scale.
Yes, yes.
And I would have the same continuum physics.
Yes,
Exactly the same, right?
yes.
So-
But the loop equation, it will be more involved if you choose some more involved action other than the Wilson action.
Right.
And even in this scheme for the
So
Wilson action,
maybe I should look at these curves a little bit carefully. So where's the continuum direct? Where's the smooth part in these curves?
let me enlarge.
So weak coupling is which way? It's lambda.
Yeah, it's a lambda to 0. But
lambda to-
when you go to the lambda to 0 to get a meaningful physics quantity, you will need very large Wilson loops to get it. This is computationally demanding.
I mean, maybe, I think you mentioned, maybe if you did something like a Wilson flow lattice, can you do it for that? Yeah, I mean, the point is that eventually you want to set a scale, right?
Yes.
And you don't want to, and you want to be infinitely far from this cutoff plaquette.
Yes,
So I'm kind of confused how you-
our current framework, we are just trying to make the bootstrap cutoff larger and larger, so we will get to access to very big Wilson actions. But I think there will be better solution.
But then you will have to actually look at Wilson loops that are larger?
Yes, we can directly, for example, you try to maximize the single plaquette, right?
Yes.
By this way, you not only get the single plaquette value, you get the whole spectrum of all the Wilson, all the Wilson actions below the bootstrap cutoff. All the Wilson loops below the bootstrap
Well,
cutoff.
if you had the full solution of the MIGDAL-MAKEENKO equations, then you'd get everything, right?
Yes, but we have a solution with a length cutoff.
But you have an iteration which takes you from the single plaquette up a few lattice spacings, right?
Yes.
And I could then introduce another action, which would be exactly the same at the physical universal place, right?
Yes.
It would totally change these equations.
Yes.
So doesn't that mean you have to somehow go to, very large order of these constraints?
In principle, in this framework, yes. Yes, you need to consider very large bootstrap cutoff, but it is not length Lmax equals 16. This is equivalent to which volume size? I think it's 30, somehow like 32 to the 4 in the Monte Carlo simulation, the space-time volume. So this is already not very small.
That's a finite volume effect. I'm worried about the cutoff effect.
Yes.
Anyway, well, it's very interesting, but I have to understand it better. Thanks.
Yeah, but I want also to mention that most of the positivity conditions or the loop conditions, actually they are correct for large enough lattice spacing volume, a lattice volume. So this is actually, this is in some sense, approximately, this is a uniform bound for big enough lattice. You can understand it this way, not necessarily infinite volume, but of course infinite volume and large enough lattice. Yes.
Okay.
Okay, I'm going to cut the discussion there. Thank you, Zechuan.
Okay, thanks.
Okay, I think we have a break of 15 minutes. Zechuan, before you leave, I have a question.
Yes, I'm still here.
Do you need to use arbitrary precision in your bootstrap calculations?
Not at all. The solver I'm using is Mosaic. It is machine precision. it is very surprising that in this case, we don't really need arbitrary precision, unlike conformal bootstrap or S-matrix bootstrap.
Well, I think that that's related to the fact that the Wilson loops are of a unitary matrix and they're bounded above. So that should be something that kind of makes the matrices a little bit better behaved, right? Because the coefficients are of order 1, not of n factorial.
Yeah, in some sense, yes. But for the two matrix model I discussed in the middle, I also used a machine precision after some careful normalization of the matrix.
But there you use factorization. It's in factorization that this problem disappears. As soon as you remove factorization, when we study quantum mechanical systems, things grow like factorial in the moment. And this seems to be a numerical issue that I'm trying to understand.
I'm not very sure about it. I'm also doing some bootstrapping on the quantum system. For the current, I didn't see any problem with precision. So most of the time, I think after some normalization of the SDP to make it
one has to normalize it to, yes.
Yes,
okay.
yes. It seems machine precision is enough. It seems. Although I didn't fully understand this problem.
Okay, thank you.
Mm-hmm.
Take care.
Okay.